As a number of people missing again. Um, so first of all, I graded the exam, so you can take a look and let me just share the screen for a second. Okay. I'm not going to go over this in detail, but I posted the solutions to the exam. Most of the people got, let's see, hold on a second. Are you seeing the solution to the first problem?
Yes.
Yeah.
All right. So most of the people got this problem right. All right. And I think mostly everybody got this problem right. This one too, a lot of people got this problem right. There was actually 500s, I think. This problem here, a lot of people got this last thing wrong. Okay. In part B, if there's 120, right, the right answer was there's 120 bears, right? Because at 2.9, right, you should have been able to calculate a roughly 80 and then you add 40, all right? Well, what happens is that we're now starting with a point above 100, okay? So in the long term, right, in the long term, the number of bears has to go down to 100 no matter what. If you start above 100, it has to go to 100. And if you start below 100, the critical point is going to be 100. So if it's 120 in B, then in D, it has to go down. It has to go to the stable critical point, which is 100. All right. So the answer to C was 100, and the answer to D was down. I would think about a third of the class got this wrong. 2/3 got it right. Okay. Now, most people got this right. Let's see. Yeah. And most people got this right. Okay. A number of people messed up this problem. And for the most part, the people that messed up this problem, people don't come to class. And I'm right now, I know I'm talking to the people that do come to class for the most part. But the people that don't come to class, I noticed with the people that missed this problem. I did this problem in class. The only thing is I did it with different numbers. Okay, so I did this problem in class with different numbers, and it's also in my notes. So I was really surprised to see a number of people. Now, it's not the simplest problem because you have to figure it out. But once again, it's in my notes, and I did it in class. So I did expect everyone to be able to get this right. But a number of people got this wrong. Like I said, it has to do with the people don't come to class in general. The people got this wrong.
Wait, Professor, can I ask you a quick question about that number 7?
Sure.
I just needed a little bit of clarify of like the number of like, did we always using the rate of in or the rate of out?
No, see the rate in is 3 gallons per minute. The rate out is 6 gallons per minute.
Yeah.
So when you set up the differential equation, right, you have to take into account that the amount of gallons out is 300 minus 3T.
Yeah.
Okay.
Yeah, because it's like for this one, it tricked me. I end up like doing both in and out, and the final result it's like the same. When they're asking for part B, I get both like of them like of 100. That's why I was like really kind of worried.
Yeah. So if you said 100, I probably didn't mark that wrong. Where I marked it wrong is that if you didn't if you had the differential equation wrong, and then you had to do this integral. This integral you had to do, the reason why I wanted to give you a problem like this is this integral you had to do with an integrating factor.
Oh, okay.
Okay. So,
right.
so once again, so take a look at my solution and compare it to yours. And let me say this, if one of the reasons why I post the solution, that I'm giving you the opportunity that if you think I made a mistake grading your exam, we could discuss it. We could discuss it after class today, or send me an email and we could discuss what you think I was unfair or I made a mistake. Okay, so that's the main reason. And there's 2 reasons why I post. The other thing too is that the final exam is going to cover everything for the whole year, right? So learn from your mistakes. I do like to give problems that a lot of students messed up during the year on the final. So make sure you know how to do a problem like this if it's on the final. Okay. All right. I don't want to spend, most people got this right. So take a look at this. And like I said, the grades were very good. There was like 500s, a bunch of 98s, and the ones that got 98s, the ones that that messed up. Problem number 4. I guess it's problem number 4. Okay. All right. So let's see what I want to do now. Okay, so that's the second exam with answers. Let me talk about the next exam. Okay. The next exam hopefully will be on. Are you seeing my screen again? Let's see. Let me make sure.
Yeah.
All right. So the next exam will be on Tuesday. And so, well, what is the next exam going to cover? Well, it'll be 4 problems. Okay. One problem is going to be series solutions about an ordinary point given a differential equation. All right. So this is when you assume a solution of the form, the summation equals 0 to infinity of c to the n, x to the n. And then a series solutions about a regular singular point. All right. So this is using the method of Frobenius, where your x now is n plus r. Okay. So we did 2 problems like that. We did some, and there's more problems in my notes. All right. So, so you have 2 series solutions, one about the ordinary point, one about the regular singular point. I'm not going to ask you to do anything like radius of convergence and things like that. That's stuff that you should have did in calculus too. Okay, and then now this is the stuff we're going to talk about today. Solve initial value problem of first order differential equation using the method of Laplace transforms. Okay, so that's a first order. And then solve initial value problem of second order differential equation using the Laplace transform. Turns out the second order is actually easier than the first. The second order is normally harder, but the way the problems I've given you, is it a property that we need to get to in order to do problem number 3. All right, so it's just going to be 4 problems. The power series and the problems on the Laplace transforms are pretty simple. Okay, you're going to have more problems on Laplace transforms on the next exam. So the next exam is going to cover more of Laplace transforms. I mean, exam 4 will cover more of Laplace transforms and systems of linear equations. I don't think we're going to get into linearization and local stability. Sometimes that's covered, so it's actually an option. Okay, all right, so that's the plan. So now let's start talking about Laplace transforms. Okay.
Sir.
Someone have a question?
Yes, that exam is tomorrow, Tuesday?
Tuesday. Yeah, Tuesday after class.
So tomorrow.
Yeah.
Okay.
Tomorrow, Tuesday, right. That's assuming I get to where I need to get to on Laplace transforms. Okay, so first of all, let's, what is the Laplace transform? When we write this curly QL, and this is brackets that I have trouble writing unless I write them real slow. So the definition of Laplace transform is an integral from 0 to infinity. And notice it starts from 0. So when we solve differential equation with Laplace transforms, we know we're talking about time, okay? And we start from 0. So you can't use Laplace transforms if you're starting with something other than 0, okay? So you have to use Laplace transform when you solve differential equations, and your initial condition, your initial value of time is 0, all right? So the definition of the Laplace transform is we have s times t, and then some function, okay? And this is when s is greater than 0. Okay, so that's the definition of the Laplace transform. So now, just the first thing I want to do is just do a simple. Let me do a simple Laplace transform. Let's say we want to find the Laplace transform of 1. All right. So now my, this is just one, right? Trying to find the Laplace transform of one. So now what is this? Now this is an indefinite integral. So let me do it right. I'll do the limit as b goes to infinity from 0 to b, right? And then this is going to be e to the minus st dt, right? Okay. So what does this integral become, right? Well, this is going to be now the limit as b goes to infinity. This integral is going to be minus s minus, no, not s. It's going to be minus, right? Minus minus s to the t divided by s, right? Right. When I take the derivative of this, the s comes down, right? The s, this minus s comes down, so I get e to the minus st, right? And this is going to be evaluated from 0 to b. All right. Now, when b goes to infinity, right? When b goes to infinity, well, let me put it in. Let me write it down here. So it's going to be the limit now as b goes to infinity of minus e to the minus sb divided by s, right? Then I'm going to minus minus, right? E to the minus s0 divided by s. All right. So when b goes to infinity, right, this goes to 0. This goes to 0. And when and then t, this is a minus minus, so that makes this a plus. So this is going to be so this is just e to the 0, right? E to the 0 is just 1. So this is just 1 over s. So the first property that we have is that the Laplace transform of 1 is just equal to 1 over s. All right. And we'll see in a minute that Laplace transform, or soon, Laplace transform is a linear transform. Okay. So it's going to turn out the Laplace transform of 2, right? Let me write like this. Laplace transform of 2 is just going to be equal to 2 over s, right? And so we can actually say the Laplace transform of any constant a is going to be equal to a over s. Okay, we'll get more into that. All right. All right, so that's the Laplace transform of a, or 1, is just what we have here. Now, when we solve differential equations, you'll have a short table of Laplace transforms that you'll use. Okay. Right now, I'm just we'll see how it works. All right, let me do another Laplace transform. It comes up a lot. Let me do the Laplace transform of e to the at. All right. So once again, we put in our definition of Laplace transform, 0 to infinity, and then this is just e to the minus at, and then it's e to the at, right? That's my function now, dt. And now I'm doing the integral, and I'm going to write this as I'm going to write this as minus s minus a t dt, right? I'm running, so it's minus s, and then when I bring the minus sign through here, it makes it easier to do the integral as people saw here. All right. So now, all right, I'll put it down here. So now if I take the limit as b goes to infinity, right? This is an improper integral, so I'll do it the right way. 0 to infinity. And let's see. 0 to infinity, e to the minus, well, I'm just putting in the limit. Right, because all I did was since it's an improper integral, I'll do it the way that we learn in calculus 2 when we do improper integrals. So this is going to be now the limit as b goes to infinity. Now this integral, right, this integral is going to be minus e, right, to the minus s minus a, right, divided by s minus a, right? When I take the derivative of this, right, it brings this down, Okay, but there should be a minus sign. Yeah, it is a minus. Yeah, that's right. Right, okay. All right. Yeah, so that's gonna cancel the minus sign with this. Okay, so now, and this is evaluated, right? This is gonna be evaluated from 0 to B. I forgot the T here. Right, from 0 to B. Okay, so so remember now the limit as B goes to infinity of minus e to the minus s minus a, put the B in now, divided by s minus a. And then there's going to be a minus minus, right? E to the minus s minus a times 0 divided by s minus a. So when B goes to infinity, right, this becomes 0. So this becomes 0. And B goes to infinity, right? This becomes 0. And I get the minus minus, it is a plus. And this is going to be 1, right? So I get 1, so this is equal to 1 s minus a. So the Laplace transform of e to the at is equal to 1 over s minus a, okay? And it should be obvious that the Laplace transform of e to the minus at is going to be a plus s plus a, right? Yeah, if we have the plus sign here, that's what we just did. We have the plus sign here. So this is the Laplace transform is s minus a. If I got a minus sign here, then e to the minus at, the Laplace transform is going to be s plus a. Okay. Any questions so far? Now I'm just doing some, okay. The Laplace transform, I'm not going to do this, but it's in my notes. The Laplace transform of sine, I'm not going to do the integral to save time. We don't need to. Because this is this, we're going to use the results. We're going to use these results to solve differential equations, right? So let's see. So this is ST sine of KT, right? This is using the definition of Laplace transform, right? My function now is the sine of KT, right? All right, so from a table of integrals, you can see that that this is equal to, that this integral is equal to b over a plus b squared a squared. And this is for a greater than 0, all right? So I'm just using this from a table of integrals, right? You could integrate this by parts, but you know, we need to, you know, if you want to do that, you could do that for practice, but that's not what's important here. So the Laplace transform then, using this integral, right? Using this integral, the Laplace transform of the sine of KT is equal to K, right? Over S squared plus K squared, all right? So from a table of integrals, we get this. This is our definition of Laplace transform. So this is the Laplace transform of the sine of KT, right? It's K and then S squared plus K squared, all right? Now, similarly for the cosine, I guess I could, the cosine, Laplace transform of the cosine of KT, that's going to just be equal to this. Now our function is cosine of KT. Just made it. All right. So now once again, I could use from a table of integrals, I get the cosine. And once again, you can integrate this by parts. This would be bx, dx. And this is equal to a squared plus b squared. And once again, a has to be greater than 0. Otherwise, if a is equal to 0, it's just 1. So this is telling us now the Laplace transform of cosine, excuse me, Laplace transform of cosine of KT is going to be equal to, this is going to be S over S squared plus K squared, right? This is S. Okay. All right, because now, right, the S is here, right? So the S is where the A is, right? The S is where the A is, and the B is where the K is. So notice the difference that the sine of KT, right? The sine of KT is equal to K, right? And then it's S squared plus K squared. And the cosine of KT is S, sine S squared plus K squared, all right? So, it's going to be a good idea to commit these to memory because it makes it, when we have to take the inverse transform, it makes it easier if you know what these are, all right? It turns out that taking the inverse Laplace transform is actually harder than taking the Laplace transform. And we'll see, you know, it's just like derivatives are easier to do than integrals. All right, so now, let's see. So now we have, let's see. All right, let me do one more. And then this is, turns out with the ones that we did, I guess I'll do this one here. It's in my notes. Laplace transform of t to the n, right? And turns out it's going to be n factorial divided by s to the n plus 1, all right? So let's see. So let's see how to do this. So it's the Laplace transform of t to the n. Now, what's important is the end result, okay? If you understand the deviation is pretty simple, but the end result is what's important. All right. So my function now, I'm just putting my function here. Remember the definition of Laplace transform, right? Here's our definition of the Laplace transform, right? So now my function is just t to the n, all right? So let's see. So I can integrate this by parts, right? So I'm going to let u equal to t to the n. Then my du is going to be equal to n, right? T to the n minus 1 dt, right? And then I'm going to let my dv equal to e to the st dt. So then v is going to be equal to minus e to the st divided by v, right? Is that right? Right, divided by s. Okay, when I take the derivative of this, it cancels that. Okay. All right. So remember now, when we integrate by parts, it's the integral of u dv is equal to u v minus the integral of v du. They have trouble. Okay. So let's see. So let's so what do I have here now? All right. So my v. So now I got. Let's see. So now I got. Oh, I guess I could put in the limit. All right, so now let me do the limit as b goes to infinity, right? B goes to infinity, and this is going to be u times v, right? So it's u times v. So it's going to be t to the n, and then there's going to be a minus sign, right? E to the minus st divided by s. Okay, and then okay, and this let me do this. This is going to be from 0 to infinity, 0 to b, right? That's this. That is u times v, right? U times v. Make sure I got this right. Okay. Now I'm going to have minus the integral from 0 to infinity of v. So it's going to be minus e to minus st divided by s. My du is t to the n. Right? My du is t to the. My du, excuse me, my du is n t to the n minus 1 dt. Okay. All right. So let's see, what do we get now? Well, let's see. When we evaluate this at the upper limit, right? When I evaluate this at the upper limit, this goes to infinity. So this is 0, right? So I hope everybody, I'm getting 0 minus 0. And then when I put 0 in here, I have t to the n. So I'm multiplying it by 0, right? Does everybody see that? When b goes to infinity, that's going to make this 0. And when I would put 0 in here for this, well, this is 1, but then this is 0. So this whole thing becomes 0. Now I get a minus minus. I'm going to make that a plus. And what I'm going to do is I'm going to make this n, I'm going to take out this n, and I'm going to take out the s out of the integral sign and make this as e to the minus, and then there's going to be t to the n minus 1 dt. Okay. Okay, so I got this minus minus that makes this a plus. I took the n and the s out, right? The n and the s are both constants, right? I'm integrating with respect to t. All right. But what is this? Well, if I take a look at this here now, right? What I got now, let me put everything here. This is the integral. What I have here now, if you look at this, this is really just n over s, and then this is the Laplace transform of t to the n minus 1, right? So now I got that the Laplace transform of t to the n is equal to n over s times the Laplace transform of t to the n minus 1. Right? Because that's what this is. This is the Laplace right here, right? This is the Laplace transform of t to the n minus 1. Okay, so what I can do now, I think it's good to derive one of these. So what I can do now, I can say that Laplace transform of t to the n minus 1 is equal to, I'm just taking this n minus 1, I'm taking this n and making it n minus 1, right? I'm taking this n now, making it n minus 1. And then this is going to be n minus 1, right? I'm replacing n with n minus 1 divided by s, and then the Laplace transform of t to the n minus 2, right? And then I can say the Laplace transform of t to the n minus 2 is equal to n minus 2 s, the Laplace transform of t to the n minus 3. Okay, so I can keep going, and I'm going to get Laplace transform of t will be equal to 1 over s, Laplace transform of t to the 0, right? And then even I can do Laplace transform of t to the 0, which is 1, right? That's going to be 1 over s. Okay, so what does this mean now? This means that if I take a look at these and string these together, this means that the Laplace transform of t to the n is going to be equal to n s times n minus 1 s minus times n minus 2 s times well, dot up to 1 over s, right? So what I'm finding now is that the Laplace transform of t to the n, and this is what's important now, is equal to n factorial divided by s plus, right? When I multiply all this out, right? So I'm showing you now that the Laplace transform of t to the n, right, is equal to n factorial divided by s plus 1. All right. So notice now, remember, we already determined that the Laplace transform of 1 was equal to 1 over s, right? So if I put 0 in here, right? If I put 0 in here, that's 1, right? Laplace transform of t to the 0, that's the same as the Laplace transform of 1, which is 0 factorial divided by, divided by this would be 0, n is 0. So this would be s, right? 0 factorial is 1, right? So it's actually consistent with what we already learned, that the Laplace transform of 1 is 1 over s. That, but the key thing that I want you to know, if you understand the derivation, that's fine, that's good. But this is what you need to make sure you understand, that the Laplace transform of t to the n is equal to n factorial divided by s plus n. That's it. You need to make sure you understand that. Okay, so now we got the Laplace transform of a few functions. Let's see how we're doing on time. Okay. All right. So in my notes, let's see how this works out. In my notes, I have I got a short table of Laplace transforms. We got this one here, that 1 is equal to 1 over s. You know, we know now that Laplace transform of e to the at is equal to 1 over a minus s minus a, right? Laplace transform of the sine of kt is equal to k over s squared plus k squared, all right? And that the Laplace transform of cosine is equal to s over s squared plus k squared. That's cosine. And then we did the Laplace transform of t to the n is equal to n factorial divided by s to the n plus 1, where n could be 0, 1, 2, dot, dot, dot. All right, I think that's clear. All right, so that's a short table. So now we have a short table of Laplace transforms. Okay, so now hopefully the next thing is pretty obvious, that integrals are linear operators, right? Actually, integrals are linear operators and derivatives are linear operators. So you'd expect the Laplace transform to be linear operators. So in other words, a property of the Laplace transform, let's say you go from 0 to infinity of e to the st. And now I want to find the Laplace transform of multiplying it by some value alpha, right? Plus, say, some beta, I'll call this g at t, that, okay, so it turns out that the Laplace transform of this, right, is the same as, hopefully this is obvious. I forgot the dt. And so it'd be plus beta. Okay, so if we have the Laplace transform, something that looks like this, right? We could break it up into, we could factor the alpha out of the integral sign, and it's just a sum, right? So this is what we mean that it's a linear transform, okay? So in other words, if I have this, right, if I want to take the Laplace transform of alpha, right, some scalar alpha times, and then beta, right? Okay, so this is just going to be equal to alpha right? I can take the alpha out, alpha times the Laplace transform of f of t plus beta times the Laplace transform of g of t. That's all we're saying here, right? So if I have something that's more complicated, we could break it up like this. I could, take out the constants, right? And find the Laplace transform of each one of the functions individually. Okay, so now let's do a problem. Okay, I wanted to keep this table here. So let's do a problem. I guess you could see the, okay. I want to see that whole table. Let me see something. All right. So let's say now I want to find the I want to find the Laplace transform of this thing. Okay, I want to find the Laplace transform of this. So I'm going to do it step by step, but you'll be able to do it all, just so you know what's going on here. So it's okay. So it'll be the Laplace transform of this, right? Taking Laplace transform, right? Now I could take the Laplace transform of this. I can write this as 2 plus 3 squared plus 4 right? That's all I did. So I'm taking the Laplace transform of 2. We're going to take the Laplace transform of this. So now this is just going to be 2 over s, right? Everybody see that? This is just 2 over s. This is going to be 3, right? This is going to be 3. But now I want to use this property here. So this is going to be 3. So this is going to be 2 factorial, right? 2 factorial divided by, now n is 2, right? N is 2 here. So this is going to be s cubed. And then plus 4. Now the cosine, so this is just going to be 4s, right? And that'll be s squared plus 16, right? S squared plus 16. Okay, so that's it. So the Laplace transform of this thing, right? I guess I can simplify this a little bit. I can write this as 2 over s plus, this will be 6 over s cubed plus 4s divided by s squared plus 16. So that's it. Okay. Right. So actually taking Laplace transforms is easy. It's the inverse that becomes difficult, or can be difficult. All right. Okay, so we're making good progress. Any questions though before I go on? I want to get to solving a differential equation. Okay, now in order to solve a differential equation, let me hold on to this. In order to solve a differential equation, I need to know what the derivative of what the first and second and third, if I want to solve a third order differential equation, we're only going to solve first and second. So if we want to solve a differential equation, we need to know what the derivative of a function is. All right. So now we're going to determine what the derivative of a Laplace transform of a function is. And then with that information, we'll be able to solve differential equations. As we also need some other properties, but we'll get to the other properties probably later in the week. All right. So anyway, so now I want to find the Laplace transform of the derivative. Okay. So let's see. So I'm going to write this as and this is going to be the derivative. Okay, so I want to evaluate this integral. Okay, so what I'm going to do is I'm going to integrate this by parts. I'm going to let u equals to e to the minus st, right? And then my du is going to be equal to minus s e to the minus s t dt, right? And then if I set dv dt, I'll do it this way, is equal to df dt, right? That's equal to my f prime. So then v is just equal to f, right? If I set my dv, right? Yeah, then my v is just equal to f, right? If the derivative of v, the derivative of v respect to t is equal to the derivative of f with respect to t, then v is equal to f. All right. So now I'm going to integrate this by parts, right? So let's see. So I'm going to write this as the limit as b goes to infinity. And let's see. Okay, so my well, let me remember, when we integrate by parts, it's right, it's the integral of u dv minus equal to u v minus the integral of v du. All right. Okay, so I'm integrating by parts. By going off the page. Okay, so let's see. So I got u. Where's my u? This is my u. So my u is e to the minus st. My v is yeah, my v. Yeah, my v is just going to be f of t. Right? That's this is u. Okay. Okay. F of t. All right. And this is we're evaluating this from 0 to b, right? Evaluating this from 0 to b. Then I got minus the integral, and this is going to be f of t, right? Now I got v times du, and so let's see, I'm going to have a plus here. You have this s, then I have an e to the minus st dt. See, is that right? Yeah. Okay. Okay. All right. So let's see. So my v, this is my v. Right. V is in, okay. And then this is the okay. Yeah, my du is this, and I got okay. I got the minus here and the minus here, so that makes this a plus. Okay. Now, all right. Now, let's see. When this goes to infinity, right? I can write this out, but when this goes to infinity, this is going to become 0, right? So when this is evaluated at b, this becomes 0, right? This becomes 0, right? But when this is evaluated at 0, right? When this is evaluated at 0, this becomes 1, right? And so we get minus f of 0, right? Whatever, turns out that's going to be our initial condition. So, okay, so this is just f of 0, all right? Then I get plus now. Now let's see, plus now. I'm going to write this as s f of t. Right? I just took the s out of the integral sign. All right. So once again, remember what we're evaluating here. This is the right. Okay, so I just took the s out of the integral sign. But what is this? Well, what is this? This is just s, and this is just the Laplace transform of f of t. Right? This is just s times the Laplace transform. This I could take this s out of the integral sign because I'm integrating with respect to t. So this is just S times the Laplace transform of f of t. So my formula now, that if I have the Laplace transform of the derivative of f of t, we normally write it like this: is it's going to be equal to S times the Laplace transform of f of t minus f of 0. Well, that's our initial, that's going to be our initial condition. Okay. Any questions so far? Okay. All right. So now we have the Laplace transform of the derivative. Right. Now we're going to use the notation that when we take the Laplace transform of a function, we're actually going to be going from time to what we call the S domain. So in other words, when we have this little f with respect to time, we're going to write that as a big F and then S, because we're going to be going from time to what we call the S domain. And the same thing, if we had something like this, if we had an X as a function of time, well, this would be a little x, this would be, maybe this is position, something like this. Then we'll write this as big X. And same thing if we had something like plus transform of, let's say, y as a function of t. When we go from the time to the S domain, we'll write that as big Y as a function of t. All right, so so I can write this, right? I could say now the Laplace transform of f prime of t using that notation is equal to S times big F of S minus f of 0. All right. So this is important. We're going to see how to use this. If you understand this, great. What's important is how we use this. How do we use this to solve differential equations? All right. So that's the first derivative. All right. Now, once you have the first derivative, it's easy to get the second derivative, right? Let's see. If I want to find the second derivative, after this, we'll be ready to solve the differential equation. If I want to find the second derivative, I can just do this, right? I need to start with this here. Right? I have this, right? I have this. As all as I'm doing is I'm taking the derivative of the whole thing. So I'm taking the derivative of this, and this. Okay. But so now if I want the second derivative, I know what this is, right? In other words, let me do this. Now this is going to be I'm replacing. Remember, I took the derivative of this whole thing, right? So I got this double prime, I got this prime, and this becomes prime. But now I know what this is, right? So I'm substituting what I have here into here. All right. So I can write this as let's see, I write it like this. I got to put an S here. Yeah, let me make sure you understand this. Okay, so yeah, so I'm going to write this as now S, Laplace transform of f of t. No, I don't want the prime now. And then minus f of 0. Yeah, f of 0. Right? That's all I did here. I'm putting what I have as f prime, I'm putting it in here. So now I get the derivative, the Laplace transform of the second derivative is going to be equal to s squared, and s squared, and then the Laplace transform of this minus s okay, that's right. These supposedly are brackets. I'm just doing them real fast. Okay, so so now I could say that using the notation, I can say that the Laplace transform of the second derivative of some function, and this is what you need to understand, is s squared, right? And then this is going to be not y. Let me make this f. Yeah. Okay, so that's it. Yeah, that's it. Make sure. Okay. All right. So the two important formulas, right? We got this one here for the first derivative, right? The first derivative is just given as a s, right? And then we're going to use the notation. When I take the Laplace transform of the function, we're going to write it as big F times F, because we're going from the time domain to the S domain. And then whatever my condition is, my initial condition, all right? So that's the Laplace transform of the first derivative. So the Laplace transform of the second derivative is this. So these are the two things that are important to know. Laplace transform of the first derivative and the Laplace transform of the second derivative. Okay, I think we could solve a differential equation now. Oh, okay. So first, yeah, we need to do the inverse. Okay. All right. So now we have Laplace transform. We're not ready yet. So we also need to be able to do the inverse, and you'll see why. So in other words, the inverse Laplace transform of 1 over s, that's just going to be equal to 1, right? Because remember, the Laplace transform of 1, right? Laplace transform of 1 is 1 over s, right? So the inverse Laplace transform, we do the inverse Laplace transform, is just equal to 1 over s. So so let's see. Okay, so in other words, so what I have we use the notation that when we take the Laplace transform of a function, we're going to write that as big F of s, right? We're going from time to s domain. And then when we take the inverse transform, we're going from the s domain to time, right? So some inverse transforms are, remember the Laplace transform of e to the at, right, was this. So the inverse transform of this is e to the at, right? The inverse Laplace transform of k over s squared plus k squared, right? The inverse Laplace transform of this is going to be the sine of kt. And the inverse Laplace transform of s over s squared plus k squared, right? That's just going to be the cosine of kt. Okay. And I guess last, the other one that we did, the inverse Laplace transform of n factorial divided by s to the n plus 1 is equal to t to the n. Okay, so so we have the inverse. We're going to see that it's not as simple as this. Many times we have to get the inverse in a form that we recognize. You'll see, if not today, tomorrow. All right. So let me do a problem. Let's do a problem taking the inverse. The inverse is actually what's a little bit harder. Okay. So let's do this. We have the inverse Laplace transform of 4s squared plus 2. Okay. Okay. How would you do this? Well, you have to remember now that that the inverse Laplace transform of sine, right? It's k over s squared plus k squared is equal to, right? We know this, right? Now, so k is actually the square root of 2, right? K is the square root of 2, right? This is k squared. So how do I get the inverse Laplace transform of this? Well, you see, the easiest way to do, let me take the 4 out, okay? I'm going to take the 4 out and write it like this. Right? Take the 4 out and write it like this. All right. Now, if I had a square root of 2 up here, that would be good, right? Because this is k squared. If I had a square root of 2 up here, then this would be the sine of the square root of 2. But I can't just put a square root of 2 up here, right? I hope you see this. So I can write this as 4, the inverse. Now I can write this as the square root of 2. I'm going to put a square root of 2 up there. But now I got to put a square root of 2 down here, right? So see, I just multiplied the top and bottom by the square root of 2. All right. So what happens now is that this is 4 over the square root of 2. Now this here, this is going to be the sine of the square root of 2 times t. Right? So the inverse Laplace transform of this is this what I have here. It's 4 times, and I guess I could simplify this too. I can write top and bottom by the square root of 2. You don't have to. So this would end up being 2 to the square root of 2 times the sine of square root of 2 times t. Okay. All right. So with the inverse, let's do another one here now. This is 1 over okay. Now remember now the Laplace transform of the inverse transform is given by this. Okay. So I need a 4 factorial up here, right? I need a 4 factorial up here. I don't have a 4 factorial up here, right? So hope everybody sees that if I have this s to the 5th, right? That means that n is 4. I need a 4 factorial here. I don't have a 4 factorial. So I'm going to write this as I'm going to put the 4 factorial there. But then I'm going to bring a 4 factorial outside. So now I haven't done anything, right? I just multiplied the top and bottom by 4 factorial. So now I got 1 over 4 factorial is equal to, this will be now t to the 4th, right? T to the 4th. And so I can write this as 1 over 24 times t to the 4th. Okay. So here's two examples. I wonder if I have more examples of taking the inverse. So you got to be careful with the constants. All right. Let me do one that's a little bit harder. How much time we got? Okay. Wonder if I'm going too fast. All right. So let's say maybe you could try this. Let me give you a minute. Now, this is more likely. We're going to do even more complicated ones, but using what we learned so far, you know, you can break this up. See if you can find the Laplace transform of this, the inverse Laplace transform of this. Let me give you a minute. Try to do it without looking at my notes. I'm just going to try to see if you can do that. Let's use the men's room. Okay. So let's do the Laplace transform of this thing. Okay. So first of all, we can use the property, right? I could break this up, right? I could break this up into the inverse Laplace transform. Let me do it this way. Okay, let me do this. I was going to skip a step. Let me do it this way. Right? I'm just breaking this up, right? Because the S, right? So I break it up into two parts. Next, I could take this 2 out. So this is, let me take this -2 out of here, right? Okay, now let's take a look at this. Let me take the 6 out. I'm going to do it this way. Let me take the 6 out. Take the 6 out. Okay. All right. Everybody see right? I just took the 6 out. Now, I really need a 2 up here. If I have a 2 up here, right? Remember now, if I have a 2 up here, yeah. Let's see. Okay. Now, here's my notes, right? I want to show you this. Okay. Okay. So I want to find the inverse Laplace transform of this thing, right? Let's see. Now we know that the inverse Laplace transform of sine, if I have I need a 2 up here, right? Here I got, so k is equal to 2 here. I need a 2 here, right? So I can put a 2 here and then put a 2 here, right? I could do that. I'm multiplying the equation by 1. So I put the 2 here, I got a 2 here. Now what is this? Well, this is just minus, this here now is cosine, right? I got the s, right? And my k here is, my k is 2, right? This is k squared. So my k is 2. So this is minus 2 cosine of kt, right? And then this is going to be plus 3. And then this is going to be sine of k. It's going to be sine of, this is 2t, right? The k here, this is k squared. So this is going to be 2t. And then this is going to be, now I got the 2 here, so 3. And then this will be the sine of 2t. Okay. All right, so that's what the inverse Laplace transform of this thing here, right? Right? The inverse Laplace transform of this is this here. It's 2 cosine of 2t plus 3 sine of 2t. All right. Now, I'm not going to draw the diagram into my notes. When we solve differential equations using the method of Laplace transform, now we're going to solve a differential equation. And the one I'm going to solve now is about, if you could understand the one I solved now, you'll be able to do one of them on the exam. But the way we solve differential equations with Laplace transforms is that we apply the Laplace transform to the differential equation with the initial values, right? And then we transform the differential equation to become an algebraic equation in y of s. In other words, if we're talking about some function of y, you know, our derivative is in terms of some function of y. So then we're going to transform the differential equation to an algebraic equation, and then we're going to solve the algebraic equation for y sub s. Then we're going to take the inverse Laplace transform, and then that's going to be the solution to our differential equation. Okay, so that's how the process works. Your book has a very similar flow chart like this, but when we put it in practice, you'll see it's pretty simple. All right, so let me solve a differential equation now. Okay, and you're going to have one on the next exam. We'll have a differential equation that's about as hard as the one I'm going to do now, and it's very easy. But on the next exam, you will have harder ones. Okay, I just want you to understand what's going on. Okay, so let's solve a differential equation. So let's say here's the differential equation I want to solve. And let's say we're given the initial conditions. Let's see. We're given the initial condition that, okay. Okay, that's our initial condition. Now, real quick, let me solve. We know that I can solve this differential equation, right? This is n squared plus 4. Now, on the exam, you have to solve it by method of Laplace transform. You can't, even though this is one you can solve, right? And it, I'm solving it the old way, right? So this tells me that that x of t is going to be equal to c1 cosine of cosine of 2t plus C2 sine of 2t, right? And that's my initial condition. So, so let's see. So when I put in 5 here, and this is C1, okay, and then plus this is going to be 0, right? Then we take the derivative of this. This will be right. I'm solving it the old way. There's a 2 here. Okay. So, all right. So now when I put in this is 0, this is going to be 0, right? And this is 1. So I'm getting this C. I'm getting here that C2 is equal to 0, right? Because this has to be 0, right? My initial condition is that that this is 0. All right. So the old way of solving the simple differential equation, I get okay. All right. So now let's solve the same thing using Laplace transforms. All right. So let me get another sheet of paper. Does that fit it there? Well, let me get another sheet of paper. Okay. Okay. I won't skip a step. So we take the Laplace transform of our differential equation. All right. So I'll do step by step. So this is the, although many times you may want to skip steps. I just take it from doing term by term. Plus transform is 0, 0, right? If you look at, if you multiply by 0 and you plus transform, it's going to be 0. All right. Okay. So now remember now, what is the plus transform? This is going to be s squared, right? This is going to be s squared, right? Maybe I should remind you. So let me find it in my notes here. Okay, here we go. Right. So right, the Laplace transform of the second derivative is given by this this here, right? We could use this here, right? But it's x, so it's going to be s squared, right? Minus f of this is s now of minus f prime 0, right? Like that's what we learned that that's how we take the derivative. Okay, so well, I should have used x, right? I should have used x. Right now, this is 0, right? This is 0, and this is 5, right? This is 0, and this is 5. So this is Laplace transform is equal to s squared, big S, right, minus s, and then this is 5, right? This is 5. Okay. All right, and the Laplace transform of x, right? That's just big X times s, right? When this is a function of t, right? We're going from the time domain to the space domain, well, S. Okay, so now what do I got here now? So I got S squared minus 5S, right, plus 4 right? That's what I have. So far, so good. Okay, so now I have to solve this for x, x, which is the function of S, right? This big X. I have to solve for this, right? So let's see. So let's see. Well, let me bring this over to this side of the equation. Right? I just brought this over to this side of the equation. Now I can factor out right? I just factored out the big X S, right? I just factored that out. So now, let me bring it up here. So now I got S plus 4. Okay, so now I got so once again we take the Laplace transform, right? And after we take the Laplace transform, we want to solve for the S of X, right? We want to solve for this. So you're going to have this in more than one place. So that's what I did. I solved for this. Now we take the inverse Laplace transform. Take the inverse Laplace transform of both sides. And what is this? Well, the inverse Laplace transform of this is this X of t, right? You know, this is, I should write capital and small, but this is X of t, right? Remember, that's the notation we're using, the inverse. And what is this? Well, let's see. I could take a 5. I missed an S, right? Missed an S. Missed the S here. I could take this 5 out. If I take the 5 out, well, let me take the 5 out. And what is this? Well, this is just cosine of 2t. So that's my answer. My answer is that that's the answer. And that's let's see, and that's what we got. So this is what we got, you know, using the method of undeterminate coefficients, right? And here we got the result using the Laplace transform. Okay, so you will have a problem like this. It's about as hard as this on the next exam, which will be on Tuesday. And we'll do some more practice tomorrow, but we still got time today. Okay. Any questions before I go on? Are there any questions? So once again, it's you know, I once had a student that that didn't use a table of Laplace transforms, and he spent an enormous amount of time and got everything right, actually. But you know, you don't have to when you take the inverse transform, you don't have to start from first principles, right? You're just going to, you need to know you need to know the table that I showed you, right? You need to know these inverse. All right. But you could use these. You don't have to solve these. Okay. Let me make that clear. You'll be able to use this when you solve the differential equations. And the same thing when you take the Laplace transform, you'll use, let's see. Where is it? Well, you're also going to need this, right? If I give you a differential equation that has a second derivative, right, you'll need this. And if it just has a first derivative, you'll use this, either this or this, right? Okay. Remember, the notation is that when we go from time, when we want to write it as the plus transform, we make it big F. And here it's little f. Using the same notation that you both use. Okay, let's see. Do I have time for another problem? I don't know if I could finish this problem. All right, let's let me do a harder problem now. If I could try to finish it. Okay, so here's the differential equation. Now we want to solve this differential equation. That's 3. Okay. Now we're going to get into this probably later in the week, and it won't be on the exam, but you know, the problem that I just did, you wouldn't solve by Laplace transform because it's actually easier to do. And even this problem is easier to do with the method of undeterminate coefficients or variation of parameters. But it turns out we're going to learn that one of the types of problems you can solve with Laplace transforms, and we're going to get into this on Wednesday, is that, you know, if I have piecewise continuous functions, in other words, if I have functions that look like this, okay, suppose I have a step function or a ramp, or I have a spike, all right? You know, this is a piecewise continuous function. The second derivative is discontinuous, but the function is continuous, right? But the first derivative is discontinuous. It turns out that if I have waveforms that look like this, I can use Laplace transforms to solve that. So it becomes a very powerful method for like electrical engineering and also for control theory, where you have pulses and ramp functions. So that's the real advantage of Laplace transforms, is being able to deal with piecewise continuous functions where the first derivative is discontinuous. Okay, but right now we're just showing that the method works and dealing with differential equations that we can solve by using the method of undeterminate coefficients. All right. So anyway, all right. So this differential equation here, let me save a little bit of time. I'm going to write this as y double prime minus 3 y prime plus 2 I don't know if I'm going to get this problem done. 2 y. Now this one here, when I take the Laplace transform of this, right, this is just going to be s plus 4, right? Remember now what the Laplace transform is of from our table, right? If this was a plus sign, this would be minus. So it's a minus sign, so this is a plus. All right. So let's see. So the Laplace transform of this is going to be s prime, s squared, big S. And then it's going to be minus s. I'm just using okay, I'm just using what we learned, right? This is the second derivative. So I can write this as s squared, and then this is big S. Now this is my initial condition. This is just going to be S, right? This is y of 0, so this is just S. And then this is just going to be 5. Right? Okay. So now I also have this, so now I also have the first derivative, right? And this is going to be s, and then this is y of 0. But y of 0 is equal to 1, so okay. So now I have, I got the second derivative, I got the first derivative. I can put it into this equation here. Let's see. So I'm going to get now here I got this -3. So got to make sure I keep the -3, and then I get a +2. Now this here is just right. This here is just okay. All right. So let's see. So now this is y squared. Here I got a let's see. Let me not. I'll make a mistake if I. So this time this is going to be -3 s, and then this is going to be +3. Is that right? So I brought in, this is right. This -3 here is times is times this thing, here. So okay. All right. So let's see. What's the easiest way to do? Okay. I could bring this s over to this side of the equation, and so I have an s here, and I also have a -2, right? So so let's see. I'm going to bring the s over, right? This s, and here I got a -5 and a -3. That's a -2. So when I bring it over here, it's going to be a +2, right? So that takes care of this and this. Okay. So I'm left with on this side. So equal to that. Okay. So far, so good. Okay. All right. Need another sheet of paper. Okay. All right. So now I want to solve this for y of s, right? So this is, I'm just factoring this out. Okay. Let's see, this is a 3. Okay. All right, so now I got that. All right, so that I got that now. So that's where I am now. So now I got y of s. Let's see, this is going to be s plus 4, s squared minus 3s plus 2. Okay, so now I got to figure out what this thing is. Okay. Now, I could factor this. One of the things that you're gonna learn that factoring and completing the square, and when you solve these type of problems, it's the algebra that you need to know is how to factor, how to complete the square. We're going to see that we need to complete the square in some of these problems, and also partial fraction decomposition. Okay, and I guess we're going to use partial fraction decomposition in this one. Okay, so we need to figure out what the heck this thing is. How can I, what is this? All right. So when you have something like this, the first thing you're going to factor this. I can factor this into S, right? I can factor this into, well, let me write this. I'm going to factor this S squared minus 3S plus 2. And these do take a little bit of practice. I can factor this into S minus 2 and S minus 1, right? That gives me the middle term. Okay. So now, let's see, I can write this as S plus 4, S minus 2, S minus 1, plus S plus 2 over S plus 4 over S minus 2. Nope, oh, wait, S, S minus 1. There's no, I don't have the, here I just have S minus 2 and S minus 1. Okay. All right, I want to get a common denominator, right? I want to get a common denominator. So the way I can get a common denominator is that I can multiply, let's see, yeah. If I multiply the top and bottom, this here, multiply this and this, right? Now I got a common denominator, right? Does everybody see that? If I multiply, here I got the S plus 4, here I got S minus 2, S minus 1. I want to get these under a common denominator. So now, okay, let's see. This here is going to give me, I'm going to skip a step and I'll explain it. Let's see, this is going to be 6 and then plus 9. Now, how did I get this? This times this gives me an S squared. This, the middle term is going to give me a, the middle term is going to give me a 6S. And then this times this is giving me an 8, right? 2 times 4 is giving me 8. But here I have a 1, right? Remember now, these are all over a common denominator. So 8 plus 1 is going to give me 9. Okay. All right. So, okay, so what do we do now? Well, now, how much time we got? Oh, we're running out of time. Well, I think maybe that's the hard part. Let's see. Okay, so here's where we are. I just went to my notes now. So we got this here now, right? So I think everybody understands this, so I guess we're good. Maybe this was the hard part. Well, this is the new part, right? This is all new stuff that we learned today, all right? But now we know how to break things up into partial fractions. So I can break this up into partial fractions, right? I can break this up into like this, right? If I have S, S minus 2, S minus 1, S plus 4. I could break this up like this, all right? Now, gotta get the next, find the next one. I know some people work in, so so we break it up into partial fractions, and then this is what we get, right? If I multiply, everybody knows how here to here, right? You multiply everything through denominator, right? Then you're gonna get this, everything here is gonna cancel, and you're gonna end up getting this. And then if I set S is equal to 1, right? If I set S is equal to 1, then this term goes to 0, and this term goes to 0. And then when I put 1 in here, I'm gonna get 16. Get 16 in here. If I put 1 in here, I'm gonna get minus 1 times 5, right? So I'm getting that 16 is equal to minus 5b. So b is equal to minus 16 over 5. And the same thing here. If I let s equals 2, then this is 0, and this is 0. And I'm getting, I put 2 in here. When I put 2 in here, I'm going to get 25, right? I'm going to get 25 in here. And then when I put the 2 in here, this is going to become, let's see. Yeah, this is going to become 6 times 1, which is 6. So then A is equal to 25 over 6. And then we do the same thing for C. We put in S is equal to minus 4. So this goes to 0, this goes to 0. And when I put the minus 4 in here, this is going to become 1 minus 4. It is, okay, that become 1. And I'm going to C is equal to 1 over 30. So now I get this. Okay. So what's going on here now? All right, so this turned out to be pretty straightforward from here. So S minus 2, right? So now I take the inverse Laplace transform of this, right? The inverse Laplace transform of this is just y of t, right? That's the inverse Laplace transform of this. The inverse Laplace transform of this is, you know, it's 25 over 6, but the inverse Laplace transform of this is e to the 2t, right? E to the 2t. This is going to be e to the t. And then this one here is going to be e to the minus 4t. So that's my answer. This is the solution to the differential equation that we started out with. Okay. So to do the exam though, there's one more property that I haven't discussed. I'll discuss that tomorrow. And then we'll do some more sample problems. And you should be able to, like I said, the first problem, if you understood the, problem that I did, you have a problem just like that on the second order differential equation that you have to solve using the Laplace transform. Okay. All right, sorry I kept you a little late, and don't miss tomorrow's class. I'll see you all tomorrow.
Hey, Professor.
Yes.
I was wondering if we're still doing the MATLAB project.
You know, I don't see how we're going to possibly get to that. How many people want to do a MATLAB project? Nobody? Let me, it's unfortunate though. We may, over the summer, it's always difficult, especially doing it remotely. I'll give you a definite answer tomorrow, but I think we may end up skipping it. Okay. But if somebody's interested in doing the project, I'll be happy to work with anybody that wants to do a project. Okay.
I would definitely consider it.
Okay. All right. Who am I speaking to?
This is Connor.
Okay.
Would it be like extra credit?
Not really. Well, let me think about it. Okay. All right. Well, have a good day.